Hi everyone. In the previous lecture, we started with our discussion on the nonlinear response of differential amplifiers to large signal differential inputs. So here are a few results which I want to summarize about what we discussed in the previous lecture. I'll very quickly summarize them. We assumed that these are differential pairs with voltage biasing. That's what we analyzed predominantly in the last class. And we assumed that we are applying a common mode DC input plus a small signal input Vi by 2. And to the other side, we are applying VCM minus Vi by 2. And then we derived some simple expressions for the currents I1 and I2. I1 is flowing on one side and I2 is the current flowing on other side of the differential pair. Whether it's a MOSFET or a BJT, we finally derived some very simple conclusions from the analysis. We said that if you compute I1 here happens to be the current on one side. I1 contains a DC component, which is the current which is flowing through the circuit when there is no differential input, when Vi is 0. Plus, it also contains an even component, IE of x, where x is a function where I can probably write it as IE of Vi. And it also contains an odd component, IO of Vi. So we said, for example, what I've shown here is the expression we derived for the collector current of this transistor I1 and collector current of I2. And we saw that I1 was I0 by 2 times e power Vi by 2 Vt. And I2 was I0 by 2 into e power minus Vi by 2 Vt. So when you expand the series, I've written this for a BJT. We derived a similar expression for MOSFET as well, which will be a square law dependent characteristic. What you have to look at is the idea behind them, not the equations, is that you can split the currents I1 and I2 into three different terms. The first term is a constant current, which is the DC current which is flowing in the circuit. If you don't apply any differential input, Vi equal to 0, that's the DC current flowing in both the transistors. That will be I0 by 2. The current is going to split equally. The second term is the even component of the current. So this will depend upon Vi and it will contain terms which are proportional to even powers of Vi. And then the third term, which is the odd powers of Vi. So for we just saw that as far as the small signal is concerned, if assuming Vi is a small signal, the source node voltage for both, or the tail node voltage, I'm going to call this as the tail node voltage for both the MOSFET and BJT based differential pair is at ground. That cannot change in response to the differential voltage Vi. If I assume that condition, then one very important part to understand here is that the input is applied symmetrically to both the transistors. That is, if I apply Vid as the differential input, which is equal to Vi in this case, half of it will appear across one transistor and the other half will appear across the other transistor. And the interesting thing to note here is that the polarities of both the VGSs are exactly opposite. I'm stressing the point here that the input will distribute symmetrically. The reason being that when we discuss current bias differential pairs, we will see that that is no longer the case. The input will no longer distribute symmetrically as you keep changing or as you keep increasing the differential input magnitude. For a voltage bias differential pair, the input does distribute itself symmetrically. So if for one side of the MOSFET it's plus Vi by 2, for the other side it's going to be minus Vi by 2. Because of this condition, we can directly say that IE, the even harmonic currents flowing in both these devices, will have same polarity and same magnitude because they both are identical transistors. Since we are looking at the even components of the current, they will be even powers of Vi. So even if the input is negative, when you square it or when you raise it to an even power, it will have same magnitude in both the sides. So IE of Vi in both I1 and I2 will have same polarity. But the odd component, because the inputs are applied in or in a differential fashion, if for one side the input is plus Vi by 2, the other side the VGS will be, the gate to source or the base to emitter voltage will be negative. So the odd terms will be of opposite polarity with each other. So using this very simple understanding, we then saw how does the current split, where does the even harmonic current flow and where does the odd harmonic current flow in the circuit. So first let's look at the odd harmonic current. So I'm first ignoring the DC component I0 by 2 and I0 by 2. So I'm assuming I0 is the current that's flowing through ground here. So half of it, I0 by 2, will flow through one MOSFET and I0 by 2 will flow through the other MOSFET. And this current I0 by 2 comes entirely from the supply. I0 comes from the supply. So supply will be providing I0, which will split as I0 by 2 on either sides. And again, they'll combine at the source or the tail end and flow into the ground. So this is how the DC current I0 flows. And the odd harmonic current flow in a loop that's shown here, both in a MOS circuit and in a BJT circuit. They loop around the differential pair. Meaning, what does it mean is that if you draw the odd harmonic part, so this is, for example, let's consider the first term, which is GM times VI by 2. So I1, if I do a pure small signal analysis, we said this guy is going to carry a current GM VI by 2. This guy will carry a current of minus GM VI by 2. So I can simply reverse the direction and show it as this way. So you will have a current GM VI by 2 flowing this way. So if you look at the small signal current, the first harmonic current, none of it is flowing into the ground. So it will just loop in this way. And in the same way, I can say that none of the small signal the odd harmonic current is going to flow through the supply as well. Because any current that's entering here, since its polarity is same here, it has to leave. So no current flows through the supply. So as far as supply is concerned, there will be no odd harmonic currents which will be drawn from the supply. The odd harmonic currents will form a loop this way. Now if you look at the even harmonic current on the other side, the even harmonic currents, both of them have same polarity. So if I assume beta and Vi square, some alpha times Vi square is the even harmonic current, both of them are going to flow in the same direction and both of them will flow into the voltage source at the source terminal or the tail terminal into ground. Since both have same polarity, like the DC current I0 by 2, the even harmonics, both of them will be entirely drawn from the supply. Supply is going to provide for all the even harmonic currents. So all the even harmonic currents come from the supply, divided into two halves and flow again into the ground. The important thing to note here is that both these transistors, whether it's a BJT or a MOSFET, both of them are going to carry both even component I0 and odd component. They both are going to carry both the even component and the odd component. The interesting thing to note is that if you consider the differential current, so which is I1 minus I2, that will only contain odd components. And if you consider the sum of the two currents, the common mode current I1 plus I2 by 2, that will only contain the even harmonics. So this is what we discussed in the previous lecture. Just to summarize, if you take the outputs differentially, in a differential voltage biased differential pair, it will only contain odd harmonics. There will be no even harmonics. And we said that's the defining characteristic of a differential amplifier. That if in any differential amplifier, if you look at the differential current or the differential voltage, it will have no even harmonic components of the input. And if you looked at the common mode component I1 plus I2, in this circuit it contains only even harmonics. And I just said what is the trajectory, the path of those even harmonic and odd harmonic currents. We said the supply is going to supply only even harmonics. Even harmonic currents will flow through the supply. Odd harmonics on the other hand will loop around this way. They will form a loop as shown in the circuit. The third important point is that the differential voltage Vi will distribute itself evenly between the two transistors. So as I increase my input differential voltage Vi, half of it will appear across one device, and the negative half of it, minus Vi by 2, will appear across the other device. So these are the three important points we discussed about a voltage biased differential pair. Now we will compare this to a current biased differential pair and similarly draw all these interesting conclusions about how does the input get distributed, what is the currents I1 and I2. So here when I write I1, capital I1 represents both the DC current and the large signal current. So here it will be, I can write it as I0 by 2 plus small I1, and I2 can be written as I0 by 2 plus small I2. The currents small I1 and small I2 here represent the signal part of the current. It can be both odd and even harmonic current, but the signal part of current. So if Vi is not 0, if Vi is not 0, then I1 and I2 will be non-zero. If Vi is 0 here, then both I1 and I2 will be 0. So these are signal dependent currents. I1 and I2, small I1 and small I2 are signal dependent currents, and I0 is the DC current. So using the same notations, we will now analyze it for a bipolar differential pair with current biasing. So this, I am following the same notations. I1 here represents the total current, which is the signal component plus the DC current, and I2 here is the signal current plus the DC current in the other half of the BJT. The sum of the two currents, I1 plus I2, is always constant because it's a constant current biasing circuit. And the differential voltage in this case, in case of a current biased differential pair, is simply equal to VBE1 minus VBE2. And that we said can be directly found from a Kirchhoff's voltage law in this loop. If you apply a simple Kirchhoff's voltage law in this loop, we can directly show VID equals VBE1 minus VBE2. Now what I'll try to do is that I'll try to express I1 and I2. The only known values in this in this analysis is I0, you know the DC current, and you also know the input differential voltage you are applying. So we want to see how does I1 and I2, the currents in I1 and I2 change when you apply a differential input voltage. If no current, no input VID was 0, then we know I1 is simply equal to I2, that is equal to I0 by 2. Now this is well known. Now we will see what happens when you apply a differential voltage. How does the currents I1 and I2 change? Then I'll also look at small I1 and small I2, which is if you subtract the DC component out of it, I0 by 2, I'm going to call them small I1 and small I2. You subtract the DC content I1 by 2 out of them, then we will look at how does I1 and I2 look like in the circuit. So first I1 is simply given by Is e power VB1 by Vt. So I'm assuming an exponential relationship for a BJT here. So it's very simple to derive for a BJT. So I'm starting with that. And I2 is given by Is e power VB2 by Vt. So this is the other equation. I1 plus I2 is given by I0. So I'll write I1 plus I2. So I'll write I1 plus I2. I'll substitute these values here. So I'll get I1 e power VB1 by Vt plus I2 e power Is e power VB2 by Vt. That's the I2 here. So you add the two terms. So that's what I've written here. Now I'm going to take e power VB1 by Vt common out. If I take common e power VB1 by Vt common out, I'll be left with 1 plus e power VB2 minus VB1 by Vt. That's nothing but I1 into e power 1 plus e power minus VID. So VB2 minus VB1 is simply minus VID because that's how we define VID. VID is simply VB1 minus VB2. So what we get here is that I1 into 1 plus e power minus VID by Vt is equal to I0. So you get I1 equals I0 by 1 plus e power minus VID by Vt. In a similar way, we can derive I2. You will get I0 upon 1 plus e power plus VID by Vt. Now both the results make intuitive sense, because you'll have to bear with little bit of mathematics here. Eventually I'll derive some very simple and intuitive results, so we can then look at the final expressions and draw the intuitions for the circuits. Now these currents, even if you look at these expressions, they make intuitive sense, because if you increase VID, if you assume VID is greater than 0, then I1 has to increase, because the gate of one of the transistors is positive, the other one is negative, or base is negative compared to the other. So I1 has to increase and I2 has to decrease. So if VID is greater than 0, e power minus VID will decrease. So you can see the denominator is decreasing, so I1 will increase. Similarly, if you look at I2, if VID increases, the denominator will increase, so I2 will decrease. So the expressions make sense, at least intuitively. Now we'll see, I'm going to make an assumption that I'm going to write VID by VT as X. So since VID by VT is X, so I can then write the expression for I1 as I0 by 1 plus e power minus X, and I2 is I0 upon 1 plus e power plus X. So now what we will do here is we'll try to derive expressions for the small signal currents I1 and I2. Now we just said I1, if you subtract the DC content out, so I0 by 2, you get the small signal current, I2, I1, and similarly the signal current, not the small signal. This is a large signal analysis. So I'm going to call I2 as the signal current, which will be I2 minus I0 by 2. So if I substitute it here, I'm going to get I0 by 2. So if I'm going to take I0 common out, I'll get 1 by 1 plus e power minus X minus half. So this will be equal to I0 by 2 into 1 minus e power minus X by 1 plus e power minus X. So I'm going to take e power minus X by 2 common out in the denominator. So I'll be left with e power minus X by 2 divided by, in the same way I'll take e power minus X by 2 common out in the denominator. So I'll get e power minus X by 2 minus e power plus X by 2 minus e power minus X by 2. Divided by e power minus X by 2 plus X by 2 plus e power minus X by 2. So it will cancel out, and this term is simply tan hyperbolic X by 2. So what I am going to get I1 as I0 by 2 into tan hyperbolic of X by 2. In the same way, I can perform an analysis for I2 as well. So this term I can write as I0 by 1 plus e power x minus half. So this reduces to 1 minus e power x by 1 plus e power x by I0. So similarly, I'll take e power x by 2 common out. I'll be left with e power minus x by 2 minus e power plus x by 2 by e power minus x by 2 plus e power plus x by 2. This expression, if you see, this is simply minus of, there is by 2 here, minus of tan hyperbolic x by 2. So this will be I0 by 2. If I just take minus 1 common out in the numerator, I will get I0 by 2 into minus of tan hyperbolic x by 2. And now if you look at these two expressions, we get I1 as I0 by 2 tan hyperbolic x by 2. I2 has an exact negative of I1. So this is simply equal to minus I1. And therefore, we said that I2 is a differential version of I1. So this is a condition which is automatically imposed in a differential amplifier. This is what we discussed in the beginning of differential current-based differential pairs itself. We said the sum of the two currents, I1 plus I2 is equal to I0. That's constant. So the signal versions, if I take the small signal version I1 plus I2, the small signal components will exactly be equal to 0. That directly follows from current biasing. So we said current biasing inherently ensures a differential operation. It forces I1 to be equal to minus I2. And that's what we derived even mathematically in a rigorous way when we showed that, we just showed I2 is equal to minus I1, and this is a natural consequence of the current biased differential pairs. It's a natural consequence of current biasing. Because we have used the constant current biasing, the signal part of the current I1 plus I2 should be equal to 0. So therefore I2 should be equal to minus I1. It's a differential version. So if I compute I1 minus I2, so I1 minus I2, you will get I0 by 2 tan hyperbolic x by 2 minus of minus I0 by 2 tan hyperbolic x by 2. So you will get I0 tan hyperbolic of x by 2. Again, x here is simply VID upon VT. So that's your differential current. And if I calculate the common mode current, so that's what I've shown here, this is your differential current. And if you calculate your common mode current, that will be I1 plus I2 will be equal to 0. Now here we need to look at these currents and start making some observations and compare it with voltage bias differential pairs. If you see the function tan hyperbolic x, so I have drawn the function tan hyperbolic x here. Now the function tan hyperbolic x exhibits an odd symmetry, meaning if you take this function and subtract it with multiply with minus 1 and reflect it around the origin, the negative half of it will just be equal to the positive half with a minus sign. I mean, if you multiply the positive half by minus 1, you get the negative half. So that's called odd symmetry. So tan hyperbolic function is an odd function by itself. So it obeys this condition, f of x will be equal to minus of f of minus x. So now what we are seeing here is that both I1 and I2 individually happen to be tan hyperbolic functions. So it was I0 by 2 tan hyperbolic x by 2 and I2 was minus I0 by 2 tan hyperbolic of x by 2. So what we observe here is that both these functions, both I1 and I2 are odd functions of Vi. So again, an odd function is something that obeys this condition, which is f of x equals minus f of minus x. So if I move x units from origin on x-axis and let's say you get a value of f of x here, if you move minus x from here, you should get minus of f of x. It should just get a negative value of f of x. So then that's an odd function. And that is easily obeyed by I1 and I2. And the important thing to notice here is that both I1 and I2 are purely odd functions of x or odd functions of Vi. And the sum of the two currents I1 plus I2 is always 0. So if you notice here in this circuit, there is no even harmonic component at all. I1 is an odd function and I2 is also an odd function. So therefore the sum and the difference will also be an odd function. So which means there is no even component, even harmonics present in the circuit at all. So if I go for current biasing, since I1 is equal to minus I2, so if any I1 increase in current in this transistor will exactly be equal to a decrease in current in this transistor. Both the linear component and the non-linear components. So when I say linear component, the small signal current Gm times Vi by 2 is a linear component. But if you expand the series of tan hyperbolic x, you will get terms involving Vi cube, Vi power 5 and so on. So these I am calling the large signal components. So what we are saying is that only odd harmonics can exist in the circuit. And that's a consequence of current biasing. So I1 should be equal to minus I2, which follows directly from current biasing, and this condition naturally enforces any signal current in I1 should be exactly equal to minus I2. This automatically enforces I1 and I2 to be odd functions. Only if I1 and I2 are odd functions, they can obey this condition. So this circuit only permits odd harmonics to exist in the circuit. Even harmonics cannot exist. And the odd harmonics will loop around the two transistors as shown here. And if you see, to ground because it's current bias circuit, the current is always going to see a constant current, the ground is always going to see a constant current I naught flowing into it. So similarly, from simple Kirchhoff's current law, I can say I1 plus this current here is small I1, this current is small I2. And I can say that if this is small I1 and small I2, so the current that's being drawn from the supply will be equal to I1 plus I2, which will be always constant and equal to I naught itself. So which means it's not containing any signal component. So even though you are applying sine waves or applying inputs at both the terminals, you will not notice any change in the current drawn from the supply. And that directly follows from the Kirchhoff's current law. You can see you are injecting current in the ground of value I naught, so you must be drawing it from the supply as well. So no even harmonics are present in the circuit. So if you compare this to a voltage bias differential pair, the voltage bias differential pair had both even and odd harmonics present in the circuit. But when you took the output differentially, when you computed the differential current, that did not contain any even harmonics. But if you see a current bias differential pair, a BJT based differential pair, if you see the circuit, it does not even contain even harmonics anywhere to begin with. There is no even harmonics in the circuit at all to begin with. It only contains odd harmonics. So that's the important distinguishing factor for current bias differential pair, and that we said the reason why it only contains odd harmonic is because of current biasing. The small signal current I1 plus I2 is equal to 0, so therefore it can only contain odd harmonic components. Now we'll look at how does this differential current and how can we define differential transconductance for this device, for this differential pair. When we plotted the differential current, which is I1 minus I2, we got the expression ID equals the differential current equals I naught into tan hyperbolic of VID by 2 VD. Now this function, for this function, what does it tell us is we are also interested in finding out what is the differential input voltage for which the current fully switches. What I have shown here, fully switches to one side when I1 becomes equal to I naught. So if you look at the tan hyperbolic function, tan hyperbolic of x, this is a nonlinear function. As you increase the value of x, if you plot the tan hyperbolic x function, it saturates as you increase the value of x. The maximum value it can go to is plus 1. So because if you see the function is this way, e power x minus e power minus x by e power x plus e power minus x. This function as x tends to infinity, these two terms will go to 0, e power minus x will go to 0. So e power x by e power x will tend to 1. So when x tends to minus infinity, similarly, you can show that it will tend to minus 1. So tan hyperbolic function has a maximum slope at the origin. It keeps increasing, but the slope keeps decreasing as you increase x, and eventually it saturates to a maximum value of plus 1 and similarly a minimum value of minus 1. So using that, you can see here for the current to fully switch to one side, fully switch when I1 becomes equal to I naught, you have to apply an infinite differential voltage. Similarly, if you want your current to be fully switched to I2, the other side, you have to apply a negative infinite voltage. But if you look at this expression, here, it is tan hyperbolic of VID by 2 VD. So this is nothing but, as I said, you can write it as e power x by 2 minus e power minus x by 2 by e power x by 2 plus e power minus x by 2. Now this expression, if you see, it will reach very close to I naught for few multiples of VT. You don't have to apply infinite VID. If you apply VID, few multiples of VT itself, the current will fully switch. For example, if I assume VID is 10 VT, if VID is 10 VT, we can say that this expression will be close to 0.99 times I naught. And that shouldn't surprise you, because we derive these results assuming an exponential characteristic of a BJT. So let's look at I1 is given by, or some current I is given by IS e power V upon Vi upon Vt. Now if I increase Vi by just 1 Vt, so let's call Vi dash as Vi plus 1 Vt, you can see that the current increases by E times. So this will be e power Vi plus Vt upon Vt. So you will get E times Is e power Vi by Vt. So your current has increased by E times if you just increase Vi by 1 Vt. If you increase Vi by 2 Vt, it will increase by E square. If you increase by n Vt, it will increase by e power n times. So even if you increase it in steps of the thermal voltage, it can increase significantly, it will increase exponentially. So that's what I mean here. If I apply a differential voltage of value e power 10 Vt, so this term will become e power 5, but that will minus e power minus 5, e power minus 5, which will be e power minus 5 will be close to 0. So this term will reach close to 1. So that's what I meant. Even if you apply few millivolts, 10 VTs, so that will be few millivolts, the current would have already fully switched to one side. We will later see about the distribution of voltages when I finish the analysis of MOSFET as well. I'll then compare the two results and we'll draw some even more interesting conclusions about the distribution of the input voltage and all of that. Now I'll finish this discussion by talking about the differential transconductance. We defined the differential current in terms of the differential voltage. So therefore the next step is to define the differential transconductance in terms of the differential voltage. So this is the transconductance which matters to us when we compute the differential gain. That differential transconductance is given by dou ID upon dou VID. That's the change in the differential current to a differential input. So if you differentiate this equation, so again I've called it dou VID by 2VT, you can call it x, and differentiate this. So again you'll have to know this result. If you differentiate tan x, tan hyperbolic x, d by dx of tan hyperbolic x, that is simply 1 minus tan hyperbolic square x. So tan hyperbolic x is an odd function, so tan hyperbolic square x is an even function. Okay, so because you're squaring it, it will always be positive. So if I write this here, if I use this tan hyperbolic square x equation, if I differentiate this equation, I'm going to get I naught by 2Vt, that comes from differentiating VID by 2Vt, times 1 minus tan hyperbolic square VID by 2Vt. Now I naught by 2Vt, if you see this term, that's your transconductance when VID is 0. If I apply 0 VID, the current will split equally between the two transistors. The collector currents will be very close to I naught by 2. So it will be ICQ upon Vt, which will be I naught by 2Vt. That's your GM for 0 applied differential voltage. So I'm calling that term as GM naught. This is the GM which we normally compute or use in our differential gain expressions, the small signal differential gain expressions. So now the GM becomes GM naught times 1 minus tan hyperbolic square VID by 2Vt. So how does this function look like? 1 minus tan hyperbolic square VID by 2Vt. How does that function look like? So if you see this function here, even before I can make intuitive sense out of this, you can look at this function here. This is your differential current with respect to differential voltage. If I differentiate this graph, you can see the slope becomes 0 on either sides. It becomes 0 on either sides. And you can see that the slope function is always increasing. The slope is always positive. And since we said this function is an odd function, the slope is going to be same on either sides. And it's going to be maximum at the origin. So that's what we get here. So it's going to be maximum at the origin. It's going to go to 0 on both the sides eventually. So the function is going to go to 0 on both the sides. And since it's an odd function, we said, if you see here, f dash of x, f of minus x will simply be equal to minus of f of x. So if you compute f dash of minus x, the negative half of it, you will get minus of f dash of x. Okay, and yeah, so minus of f dash of x. So again, I can write it as the slopes will both be same. Okay, on either sides. Okay. Okay, so here what I can show is I can directly show that this will be f dash of minus x for an odd function. For an odd function, if you take its derivative, it will be same as f dash of plus x. This is something you can very easily show, and you can even see it from graphically here. So now I'll just try to plot mathematically. So what I'm trying to show is that your GM is maximum at this point and it decreases after that. Because your slope is going to go to 0 eventually, it's a continuous function and it's monotonically increasing here from minus infinity to plus infinity. Okay, and I can say that this function will again decrease on either sides to 0. So now if I am plotting tan hyperbolic square x, if I want to plot tan hyperbolic square x, so then I can simply take this function tan hyperbolic x and square it. So this is tan hyperbolic x. If you do tan hyperbolic square, you get this graph shown in pink. So both are always positive, even the negative values are reflected around the origin, so you will get positive values. And I am subtracting 1 from it. So 1 is this constant value. If you subtract 1 minus this graph, you get this graph. So it will be 1 minus this, it will go to a maximum value at this point, it will be 0 on either sides. So what you see from this graph is that the differential transconductance is maximum when your differential input voltage is 0. As you increase your differential input, the differential transconductance also keeps reducing. On whether you make it positive or negative, the differential input voltage, the differential transconductance will start decreasing. So generally when we say small signal analysis, we are very close in this region. For small signals, for small VI by VID values, your GM differential will be very close to GM naught itself. GM naught is your transconductance at VID equal to 0. So that's it. We will now do the analysis for a MOS based differential, current based differential pair in the next lecture and draw similar conclusions.